Okay, in the last video, we kind of left it hanging that we had an area of 8 minus 8, which was an area of 0, and we talked about, with an area of 0, what does that mean? Well, we've learned in the past that a positive area means that that particular shaded region, no matter what it looks like, would be above the x-axis, and the negative area, really, we don't know what it looks like, would be below the x-axis. And what it would appear to us is if we get a 0, there's just as much area under the curve above the x-axis as there is below the x-axis. And what we want to do is just go to the graphing calculator and take a look at that to verify. Now, if you actually wanted the total area of the shade, you would say, well, the area is 16. But remember that the definite integral, we're looking for the value. So the value of the definite integral is 0. And so we want to really consider that a positive area and a negative area so that we come out with the true definite integral. So we're going to tell the graphing calculator to graph this for secant theta tangent theta. So I'm going to go to the calculator. We're going to have y equal. I need to tell it 4 times, and I'm just going to do an open parenthesis just so we can see it. Now, how do we write secant? Secant is reciprocal of. So I'm just going to do a second parenthesis, and I'm going to do 1 divide cosine to get of theta. Close it, and then I'm going to close it again. So there's my cosecant theta, and then I had tangent, right? So times tangent of that same theta, we'll call it x, close. And then I'm going to close the whole thing, so I have 4 times that whole thing, just so it looks like it's supposed to. I'm going to make the window fit the data. Now, it said from what to what?
Negative pi over 3 to pi over 3.
So negative pi over 3 to pi over 3. And I'm just going to go pi over 2. So I'm going to make my x minimum negative pi divided by 2. So second up there is my pi divided by 2. And you can see it change it to a decimal. And then I'm going to go to positive pi over 2. On my y, minimum and maximum, I'm just going to call it negative 5, positive 5. See what that does graphically. And then I'm going to hit graph, and we'll see what we get. And hopefully we have enough of what we're looking for there as far as the area. And then we're going to go to second graph, which is trace. And we're going to choose number 7, which is the definite integral. And we want to tell it the lower bound, and the lower bound is going to be negative, you said pi over 3. So negative pi, I missed that one. Negative pi, I'll try again. Negative pi up there, I hit the wrong button. Now divided by 3, enter. My upper limit was regular pi over 3. Pi divide 3, enter. And you can see the shade below and the shade above, and it comes out to be 0. So that validates what we had tried to do as far as finding the definite integral of 4 secant theta tangent theta. Any questions on number 10? Okay, it's kind of good to validate. It's amazing that the calculator can give you the answer, but we still want to be able to manipulate these things on paper. It gives us an understanding of the system and how it works. All right, so let's move into number 11. It says find the area of the region bounded by the graphs of these 3 equations. Well, at first glance, you may say, well, that looks a little bit different. We've got 3 equations, but you realize that 2 of those are vertical lines, so it's not any different than what we've done. So if we were to try to draw a picture of this, then we have we have the region bounded by the vertical line x is 0, the region bounded by the vertical line x is 2, and that curve. Now, an x cubed plus x, it's going to be some type of curve like that, right? We know that an x cubed looks like that. We have the assumption that it's something like that. And we'll graph this in a minute to maybe verify our thoughts. But you see that what we really have then, what we really have is the integral from 0 to 2 of x cubed plus x dx. You understand that we can write that as that definite integral, because what we're looking for is the area underneath the curve from 0 to 2. You see how we translated that into a definite integral equation? Okay, well, we know how to do that now with the fundamental theorem of calculus. We would actually take the derivative. We would find that f of x function, and we know that to do that we would add 1 to the exponent, which would give us an x to the 4th, and then we would divide by that same thing 4, so we'd have an x to the 4th over 4. That's an exponent of 1, and we know that we would add 1, which would give us an exponent of 2, and we would divide by that same number 2, and we would put a plus c, but we realize when we're applying the fundamental theorem of calculus, we're going to have a positive and negative c that cancel, so we can leave those out. And that's going to be evaluated, this is going to be evaluated from 0 to 2. And so if you recall, what we do is we find this function value. We find this function value evaluated at the upper bound 2 minus the evaluation at the lower bound 0, right? Okay? So that means that we're going to plug in a 2. We're going to put us a big old minus sign right here. We're going to evaluate that at 2, so we would have 2 to the 4th over 4 plus 2 to the 2nd over 2. And then our big minus sign, because the evaluation from the upper bound minus the evaluation from the lower bound. And so at the lower bound, remember we need to put a parenthesis there and distribute that negative idea. And so we're going to have 0 to the 4th over 4 minus 0 to the 2nd over 2. Okay? Now, that whole second part then becomes a 0, as you can see. And right here, we'd have 2 to the 4th. 2 times 2 is 4, times 2 is 8, times 2 is 16, divided by 4 is 4. And then we've got 2 to the 2nd is a 4, divided by 2 is 2. And all of that second part becomes a 0. And 4 plus 2 is 6. So the area of the region bounded by the graphs of those three equations is 6. Any questions on number 11? Okay. All right, let's take a look at number 12. Number 12 says find the average value of the function over the given interval and all values of x in the interval for which of the function is equal to its average value. Average value. Average value. You may think, well, what is average value talking about? Well, let me try to explain average value. The idea is that if we were to have this some kind of a graph here in a curve, and we know that this would be up 4, 1, 2, 3, 4, and it would be a parabola that is opening down, right? So it would look something like this, the graph of that, right? That parabola, that's an x square, and it's a negative, so it's opening down and shifted up 4. And we're going to evaluate that situation from -2 to +2. It doesn't necessarily hit -2 and 2, but we're looking at some type of evaluation of that. And what we're thinking is that if we were to try to create a rectangle like with this base and some height, there would be some height that we could put with that, that would create a rectangle whose area is exactly the same as the area under that curve. Okay? And so this height, remember, instead of having an infinite number of heights with an infinite number of rectangles, there's one height that we could choose, which would be the average height, the average value of height, put with this entire base, that would create a rectangle whose area is exactly the same as the area underneath that curve. Okay? And so we're going to leave you at the end of this video thinking, we left you with the last video thinking about how does the area turn to 0. We're going to leave you with this thinking, how could we find average height? When we go back to the limit process of finding the definite interval. So as we think about how we set that up, and we think about the formulas for areas, we'll try to, in our mind, conjure up a way to understand the average value equation. And we'll do that next time. Appreciate your attention.